Hi everyone, I want to do a few examples involving local and absolute minima and maxima. So we gave the definitions of local minima, local maxima, and absolute minima and absolute maxima last time. Here I'm showing you the definition of the absolute maximum and for the absolute minimum. Here's my first problem. I want to find all local and absolute extrema. And when I use the word extrema, that means minima or maxima. And again, minima is plural for minimum and maxima is plural for maximum. So look at this graph here. Do you see any minima or maxima? The answer is yes. We actually have a minimum and a maximum, and they're both local. So we have a local minimum at, well, remember for a minimum, we look for a valley in a graph. Here we have a valley. And we have a local minimum at x is equal to 0 for the valley, and a local minimum value of 0. And that is going to be the y coordinate. So the minimum, the actual minimum value is going to be the y-coordinate. The location is going to deal with the x values, okay? So when x is 0, that gives us the this minimum here, this minimum value. So we have a maximum because we have a heel here. The local maximum, so let me write this here. We have a local maximum at x is equal to -4. Sometimes you might see when x is 0 or when x is equal to -4. And a local maximum value of +4. So this is plugging in -4 into our graph. You can see that the y value corresponds to 4. There are no absolute minimas or maximas here. You can see that this graph goes on forever in this direction. So there's not going to be a maximum value because we're always, no matter what y value you find, you're always going to have a higher y value. So if you choose x is equal to 8, this graph's going to go, let's say it goes up like this, you're going to have a y value, but the further you go out when it comes to this your x values, the higher your y value is going to be. And the same thing when it comes to the minimum values. So if we go out further, we're always going to go further and further down. So there's not going to be an absolute minimum or absolute maximum. Here is our next example. Do we have local minima, local maxima, or an absolute minimum and absolute maximum? The answer is yes to both local extrema and absolute extrema. Okay, let's start with local maxes and mins. So we have a local, and I'm just going to abbreviate this to max, and local min. So we have a local max when when x is equal to, looks like 0, and a local max value of 1. We have a local min when x is equal to -4 and a local minimum value of -2. So that's 1, 2. We have another local min. We have a local min when x is equal to +4. And it looks like our y-coordinate is -3.5. Okay, we do not have an absolute maximum because you can see this goes on forever and this goes on forever. So our y values are going to go all the way to positive infinity. But we do have an absolute minimum. So we have an absolute minimum when x is equal to 4. Because you can see this is the lowest point on the graph. We don't have any y values on this graph that are below -3.5. We've seen this graph before. Let's find all the local and absolute extrema. Okay, so here we have a valley, and here we have a valley. So those two are going to correspond to local mins. So I'm going to write it like this. When x is equal to, looks like -1, and x is equal to 4, the min value is, for x is equal to -1, is going to be -2, and for x is equal to 4, it's going to be -1. We have a local max when x is equal to 2. You can see we have a hill here, and the max value is a 1. Notice also that this graph doesn't go on forever. It ends right here and it ends right here. Now for a local minimum or maximum, you have to be able to find an open interval around a number for it to be a local minimum or maximum. So in other words, for something to be a local max, it has to have a left side and a right side. So what I'm getting at is this point here, although it looks like on this side we're going up, it's not going to be a local max because I don't have anything on this side. Okay? And this is not going to be a local max as well. But we do have an absolute max. And an absolute max can occur at an endpoint. So here we have an absolute max. That's when x is equal to 6.5. And our absolute max value is equal to, it looks like 1.5. See, that is the highest point on this graph. And we have an absolute minimum, the lowest point on this graph. It occurs at x is equal to -1, and the minimum number is -2. So I'm going to actually circle what we did. So x is -1. This is also an absolute minimum. Okay, so again, local minimas and local maxima, they occur at tops of hills and bottoms of valleys. An absolute minimum or an absolute maximum, that can occur at the top of a hill or a bottom of a valley, but also at endpoints if you have a closed interval for the domain. So you see how we end here and here. Let's look at another example. So let's find all local and absolute extrema. Again, here, our graph ends here and ends here, so it doesn't go on forever. So let's write the local min, local max, okay? So this one is a little tricky. Notice that we have a bottom of a hill. In fact, the bottom of a valley. In fact, all of this is the bottom of a valley. So we do have a local minimum. This is when, let me put here, when x is any number in the interval -1 to 2. And we have a local min value of -3. Because here you can see this is -3, so that's the minimum value, but it's for all of these points here. We have a local max when x is equal to 0. Not 0, excuse me, 4. When x is 4, and the local max value of 0, because that's that top of this little hill. Okay, we also have an absolute minimum and an absolute max. So we have an absolute, I'm going to abbreviate it, min when x is equal to 8, and an absolute min value of, it looks like, -5. We have an absolute max when x is equal to -6, and an absolute max value of 2, because when it's -6 we get 2. Okay, so something you might have noticed is that a graph that ends always has a absolute maximum and an absolute minimum. So if we don't go on forever, we're guaranteed to have an absolute maximum and an absolute minimum, and we only get one of each. Okay, if we have a graph, so here's another graph that ends, you can see it doesn't go on forever, and we had an absolute max and an absolute min. But sometimes, like this graph, we only get one. We had an absolute minimum, but we didn't have an absolute maximum. And I don't think, oh, and here's another one. And here we didn't have an absolute minimum or an absolute maximum. So we're only guaranteed to have both an absolute minimum and an absolute maximum when our graph, its domain is a closed interval. So that graph ends. So it has endpoints. It doesn't go on forever. That's called the extreme value theorem. I'm going to write that down. I think it's an interesting concept. You don't really need to do anything with it, but the extreme value theorem says if a function f is a continuous function, and that just means you can draw the graph without lifting your pencil. So like this one here, see, I could draw this whole thing, I could draw it without lifting my pencil. In other words, there's no holes where I have to jump or any gaps. So if a function f is a continuous function, defined on a closed interval, just some interval a, b, so the domain looks like this, then f has an absolute minimum and an absolute maximum. So you're guaranteed to get both.